welcome to this the lecture number 35 of the course Stochastic Hydrology. Now, in the previous few lectures we have been discussing the multivariate stochastic models, which are essentially useful in generating stream flows in a let us say a catchment where you are interested in generating simultaneously flows in several streams. And these streams that we are considering may have, in fact, they do have their own correlation structure. So, you would like to preserve the correlation structure between a stream A and a stream B in the same catchment, and these type of models are essentially useful when you are planning for large scale water resources development in a particular catchment. What I mean by that is, let us say that you have a huge river basin such as the Narmada river basin or the Brahmaputra river basin, etc., where several tributaries are joining, and also you may have a hydrologically homogeneous region in which there is a correlation structure between among several streams, and then you would like to develop this entire catchment by putting let us say reservoirs on several streams and so forth. In such situations, you would like to generate flows on all of these streams, synthetically generate stream flows on all of these streams simultaneously. What do I mean by simultaneously? We have studied in our earlier courses the models such as the Thomas Fearing model, for example, in which it was a single site model. The single site models preserve the statistics of that particular stream, if we are talking about the stream flow generation. The multi-site models, on the other hand, apart from preserving the statistics of the individual streams, they also preserve the correlations, cross correlations among these different streams. If I have, let us say, if I have a catchment in which we have two streams, let us understand this correctly. Let us say that we have a catchment something like this, and then I am interested in generating flows at this location as well as I am interested in generating flows at this particular location. So, let us say I have A and B. Then we may also have a situation where I may be interested in generating flows at this location C by taking into account the correlation structure among A, B as well as C. In our single site models, what we would have done? We would have taken the flow records at this particular site C and then used a single site model such as, for example, the Thomas Fearing model, and then used the Thomas Fearing model to generate the flows which would have preserved the mean, the variance as well as the lag 1 correlation of the flows at this site. However, when we come to the multi-site generation, when generating the flows at site C, we would also take into account and indeed preserve the correlations that the flows at site C have with flows at site B as well as flows at site A. And similarly, when we are generating flows at site B, we will preserve the correlations of the flows at site B with respect to the flows at site A as well as with respect to site C. So, there is a spatial correlation as well as there is a temporal correlation. The temporal correlation is in fact the autocorrelations that we are talking about. So, when we are focusing our attention on C, for example, on the flows at site C, it will not only preserve the autocorrelations of the flows with respect to themselves across time, but it will also preserve, the models will also preserve the cross correlations with respect to flows at B as well as with respect to flows at A. So, when you suspect that the flows have cross correlations and you would like to generate flows on both these sites A and B and A and C, etc., then you need to look at multi-site models. So, we are essentially generating flows simultaneously at site A, site B and site C and so on. Now, these kind of problems will be very useful when we are talking about large scale water resources development, in which case in which situations we will be interested in simultaneous generation of flows, so that you can examine the implications of putting several reservoirs. Let us say that I would like to put a reservoir here, a reservoir here, reservoir here and so on. So, you can examine the implications of developing these kind of watersheds or the catchments simultaneously. So, in the last class specifically, what did we see? In the lecture number 34, we examined, starting with the single site model, we went on to a multi-site model, typically the Markov model, that is multi-site Markov model is what we discussed in the last class. The structure of the model looks like this: x t plus 1 is equal to E x t plus g into epsilon. Now, this is the multi-site Markov model that we have discussed in the previous class. Remember, E is not the expectation here, it is a p by p diagonal matrix, and x t is the p by 1 vectors, p is the number of sites. So, let us say that you have a case where you are talking about generation of flows in site number 1, site number 2, site number 3 etcetera. So, like that you have p number of sites. So, at every site you have a time series of flows available. These are the observed flows, and that is what defines the vector x t here. X t is a p by 1 vector of standardized values of the variable generated at time t, and we are writing this expression for time t plus 1. So, x t plus 1, which will generate at all of these p sites the flows at time t plus 1, using the flows at time t plus some random component, and E and G are coefficient matrices. Now, in this model that we have already discussed, E is a p by p diagonal matrix, which has the jth diagonal element, which is rho j 1. What is rho j 1? It is a lag 1 serial correlation at site j. And similarly, G is a p by p diagonal matrix, which jth diagonal element is given by 1 by root of 1 minus rho j square, and rho j 1 is the lag 1 serial correlation at the site j. A more general form, and which is also very useful, is the Matalas model, and this is what we introduced in the last class. Starting with this kind of a structure, Matalas has introduced a more general form of the multi-site model. In fact, in this we do not assume that it is a Markov process, although we relate x t plus 1 with x t here. The coefficient matrices A and B in fact reflect the cross correlation structure in the multi-site situation. So, this is what we were talking about in the last lecture towards the end. So, we introduced the Matalas model x t plus 1 is equal to A x t plus B epsilon t plus 1, which is similar to the Markov model that we have discussed earlier, except that the epsilon t plus 1 will be independent of x t now in this case. As we progress, we will discuss that more. So, we are talking about this particular model in the context of simulating or synthetically generating flows at several sites simultaneously. And these kind of models are typically used for large time intervals. Let us say that a seasonal flows or the annual flows etcetera, which are essentially useful for planning purposes. Now, this is the form that was given by MATLAS. This is a multi-site normal generation model, and it preserves the mean, the variance, lag 1 serial correlation and lag 1 cross correlation and lag 0 cross correlation. Distinguish between the serial correlation and the cross correlation. I keep repeating this because serial correlation is important when we are talking about multi-site models, in the sense that it has to preserve the structure of the time series at that particular location, as well as it must preserve the cross correlations with the other time series, and therefore, both serial correlations as well as cross correlations become important in this. Now, we write x t plus 1 is equal to a x t plus b epsilon t plus 1. Let us go through this model in detail now, although I would have introduced it in the last class. Now, x t and x t plus 1 are p by 1 vectors. Remember, p is the number of sites representing standardized data corresponding to p sites at time steps t and t plus 1 respectively. I have when talking about the Thomas Fearing model and other ARMA type of models, I have told earlier that we write these models always for standardized data. So, x t and x t plus 1 are in fact the standardized data. Recall that by standardization I mean deducting the mean and dividing it by the standard deviation. For example, x t, when I have a value x t, let us say I want to write x t, and the standardized value of x t, I can write this as x t s is equal to the value of x t itself, this is observed value, minus x bar, which is a mean, and divided by the standard deviation. So, all of these models, these type of models are written for standardized data. So, from the observed values you standardize the data and then we apply this kind of models. Now, there is an important assumption here is that the model is multivariate normal. It means that all the variables that you are using, all the flow variables, the x t's, they are all normally distributed random variables. So, we use this assumption, and that is why essentially we use these kind of models for large time steps, for example, annual stream flows, seasonal stream flows, etc., where the assumption of these variables being normal is justified. If you use, for example, daily rainfall and such processes which cannot be approximated by normal distribution, then your models will be wrong. So, you must keep this in mind, that these kind of models, multivariate stochastic models that I am discussing here, especially the MATLAS model in this particular form, must be used essentially for long time interval processes, such as the seasonal flows, the annual flows and so on. Okay. Now, the epsilon t plus 1 here in this expression is a normally distributed random variate with 0 mean and unit variance. So, it is n 0 1. It is p by 1 vector because you have p sites and epsilon t plus 1 is what we are talking about. So, at every site you have a standard normal deviate, and an additional assumption here is that epsilon t plus 1 is independent of x t. Your structure requires x t as well as epsilon t plus 1 on the right side. So, the epsilon t plus 1 here is independent of x t. This will be a useful assumption when we derive expressions for A and B, as we will presently see. Now, A and B are coefficient matrices, and both of these are of size p by p, as you can see here. This is p by p, this is p by p, this is p by p, this is p by 1. I am sorry, this x t is p by 1. So, you are having p by p here and p by 1, p by p and p by 1. and this will be p by 1 matrix. Now, which means what? In this model now, if you specify A and B, which are the coefficient matrices, epsilon t plus 1 is obtained from your standard normal deviates tables. So, epsilon t plus 1 can be obtained, and x t is the previous value, it is a matrix of previous values. Your model is completely specified. So, our objective now is to specify A and B in terms of the data. So, which means that if you have the observed flows at all of these p sites for some time periods, let us say t is equal to 1, t is equal to 2, etcetera, t is equal to n. So, at each of the p sites you have the observed time series, that is time series of the observed flows. We would use these observations, available observations, to determine A and B. So, that is the objective with which we will proceed now. Now, in the last class I introduced m naught and we defined m naught as expected value of x t prime. X t prime is the transpose. So, expected value of x t prime is nothing but the cross correlation matrix of lag 0, because you do not have a x t plus k here, x t prime, and therefore, you are talking about the cross correlation between x t with itself, which is cross correlation at lag 0, or in fact, it is a covariance. Now, the ijth element of this matrix m naught is therefore, from this we can write it as in terms of the data, these are the observed values of flows. So, this is x t is q I t minus q I bar by S I, where q I t is the observed flow at the site I in time period t, and q I bar is the mean of the flows at site I, which is simply you sum over all the time periods divided by the number of time periods, you will get q I bar, and S I is the standard deviation of the flows at site I, similarly for site j. So, this is m naught, that is the ijth element of the matrix m naught. Now, similarly, we will examine another matrix m 1, we will define another matrix m 1, both of which together, that is m naught as well as m 1 together will be useful in determining A and B. So, our objective of introducing these is finally to write some useful expressions, elegant expressions for determining A and B. The way I defined m naught was I took expected value of x t prime. Now, I will lag it by one time period and write expected value of x t with x t minus 1 prime. So, I will define m 1, which is a matrix p by p, as expected value of x t minus 1 prime. So, I am lagging it by one time step and then taking the expectation. Similar to what we did for the m naught matrix, the ijth element of the m 1 matrix now will be simply expected value of x I t x j t minus 1, that is ijth element. This we determine, this we are able to write because expected value of a matrix is in fact matrix of expected values of individual elements. So, that is how we write. Much the same way as we wrote m naught I j, we write now m 1 I j. So, we take the flow at ith site and the flow at jth site. This is at time period t and this is at time period t minus 1, and then we write this expression. Because we are lagging it by 1, we start it from t is equal to 2. So, I get the elements I j for I is equal to 1 to p as well as j is equal to 1 to p. We get all the elements from this expression, and therefore, m 1 is defined completely, m 0 is defined completely. Now, here I have written in terms of q, which is the flow, here I have written x also means the flow. So, x is the same as the q that we have written earlier. Remember that M1 as well as M0 are completely defined once you have the data. That means, you will be able to form the matrices M0 as well as M1 just based on the observed data. And what is the form of the data that we have? At each of the p sites, we have a time series t is equal to 1 to n. Let us say you have annual flows at each of the p site, and let us say you have 40 years of flows. So, t is equal to 1, t is equal to 2, t is equal to 3, etcetera, up to 40 years at site number 1, at site number 2, etcetera, up to site number 40. So, this is how you define M0 as well as M1. Now, once we define M0 and M1, we will now go back to our original expression, where we wrote x t plus 1 is equal to a x t plus b epsilon t plus 1, and then see how we can determine a and b using M0 and M1. So, this is M1. The way I wrote here is, in fact, these are the standardized flows. So, I will write it in terms of the original flows, which is q I t, q I minus 1, etcetera, much the same way we did for M0, except that you must remember here that these are for two different sites, which in fact is the case with M0 also. And q is the original random variable. That means, we may be talking about annual stream flow or some such thing. And from this you can see that M1 is in fact the cross correlation matrix of lag 1. At lag 1 you take the cross correlation, and M0 is at lag 0. All right. Now, we will look at this model now. X t plus 1 is equal to a x t plus b epsilon t plus 1. This is a p by 1 matrix. This is p by p, p by 1, p by p, p by 1. Now, what we will do is, just to make sure that we get expressions for a and b in terms of your M0 and M1. Do not lose the fact, do not lose the sight that M0 and M1 are completely determined based on the data. So, the moment you have data, you can determine M0 and M1, and therefore, we should be able to express a and b in terms of M0 and M1. To do that, what we will do is, we will multiply, post multiply in fact, by x t prime, and then we will take the expectation. So, I will multiply x t plus 1 with x t prime is equal to a x t prime plus b epsilon t plus 1 x t prime. I am post multiplying all through by x t prime. Then we will take a expectation. So, expectation of x t plus 1 x t prime is equal to a comes out, it is a constant, expected value of x t prime plus b expected value of epsilon t plus 1 x t prime. Now, look at this expected value of epsilon t plus 1 x t prime. We said right at the outset that epsilon t plus 1 is independent of x t, and therefore, the expected value of epsilon t plus 1 x t prime must be equal to 0. Why? Expected value of, let us say, two random variables x and y, if they are independent, will be equal to expected value of x into expected value of y, and expected value of one of the random variables is 0, because we said epsilon t plus 1 has n 0 1, and therefore, its expected value is 0, and therefore, this expectation becomes 0. So, the second term vanishes here. We get here a expected value of x t prime, and what is x t prime? It is M0. We have defined M0 to be expected value of x t prime, and therefore, this term is nothing but a M0. And what is this now? Expected value of x t plus 1 x t prime. We have defined M1 as expected value of x t minus 1 prime, and therefore, I can also write this as expected value of x t plus 1 x t prime, just lag it by one time step, and therefore, x t plus 1 x t prime, the expected value of that will be written as M1, and this is a and this is M0, this becomes 0. So, I will be able to write M1 is equal to a M0, and therefore, I should be able to get a as M1 M0 inverse. So, once you define the data, once you have the observed data, you have defined M naught and you have defined M 1. From M naught you get M naught inverse and M 1 is defined, therefore, you should be able to get A. So, A is completely fixed. So, just based on the data without doing much exercise, you will be able to get the coefficient matrix A. But the coefficient matrix A itself, because it is determined from M naught and M 1, will incorporate the cross correlation structure, because we defined M naught as cross correlation at lag 0, which is in fact the covariance, and M 1 as a cross correlation at lag 1. So, both of these are included in the matrix A, in the coefficient matrix A. Now, let us see what we do with the coefficient B. So, this is our model x t plus 1 is equal to A x t plus B epsilon t plus 1. Now, we will post multiply with x t plus 1 prime on both sides and take expectation. So, I will multiply this with x t plus 1 prime, x t plus 1 into x t plus 1 prime and A x t into x t plus 1 prime plus B epsilon t plus 1 into x t plus 1 prime. Now, we take the expectation. So, I will write this as expected value of x t plus 1 x t plus 1 prime is equal to A into expected value of x t plus 1 prime plus B into expected value of epsilon t plus 1 x t plus 1 prime. What is this now? We defined M naught to be expected value of x t prime and therefore, it is the same time step. Therefore, I will be able to write this as M naught, which is expected value of x t plus 1 prime. Then we have expected value of x t plus 1 prime and we have another expected value of epsilon t plus 1 and x t plus 1 prime. This expectation, in fact, expected value of epsilon t plus 1, if we had x t prime here would have been 0, because we said epsilon t plus 1 is independent of x t. But epsilon t plus 1 x t plus 1 prime, when you take the expectation of that will not be 0. Remember this, because epsilon t plus 1 need not be independent of x t plus 1. Epsilon t plus 1 is independent of x t in this structure, and therefore, this expectation is not necessarily 0. Similarly, we had defined x t with x t plus 1, I am sorry, I repeat that, expected value of x t with x t minus 1 prime as M 1, but this is not M 1, because you have x t and x t plus 1 prime, and therefore, we need to evaluate both this expectation, namely expectation of x t 1 plus 1 prime and epsilon t plus 1 x t plus 1 prime separately. So, let us determine these two expectations now. The left hand side is M naught. So, we will start with this expectation of x t plus 1 prime. We defined M 1 to be expected value of x t minus 1 prime. So, M 1 prime will be expected value of x t minus 1 prime the whole prime, that is expected value x t minus 1 prime. This is a matrix. So, I am taking the transpose of that. This is a matrix, I am taking the transpose of this. Now, because this is a matrix, I write this as expected value of x t minus 1 prime here, and this I will be able to write it as expected value of x t minus 1 x t prime. Why? From your matrix algebra, you should know that let us say I have a situation like this A B transpose. This will be simply B transpose A. So, here I have x t minus 1 transpose and that transpose. Therefore, I will write x t minus 1 transpose and transpose. So, x t minus 1, that are transpose of x t minus 1 transpose, which is x t minus 1, and x t transpose. So, this is from, this follows from here. I think I will have to write it as b dash a dash. Okay, that is how it becomes x t transpose here. So, I will be able to get from here m 1 dash is equal to expected value of x t minus 1 into x t transpose. So, I can also write it as m 1 dash is equal to expected value of x t plus 1 dash. Why I need this expectation from your earlier expression? I need expected value of x t plus 1 dash, and therefore, I will be able to write this as m 1 dash. So, m 1 dash is expected value of x t plus 1 dash. We are now focusing on expected value of epsilon t plus 1 x t plus 1 prime. So, we will write this term as epsilon t plus 1 x t plus 1 prime is equal to epsilon t plus 1, I will take it out, and x t plus 1 prime from our model x t plus 1 is a x t plus b epsilon t plus 1. So, from the model I write this as a x t plus b epsilon t plus 1, and I am talking about the transpose of that. So, I will take a transpose of that. So, this will be epsilon t plus 1. Again the way we wrote a b prime is equal to a dash b dash, that form we will use. Therefore, this will be x t prime into a prime plus this epsilon t plus 1 into epsilon t plus 1 prime into b prime. So, this is what we get as epsilon t plus 1 x dash t plus 1. Now, on this we take expectation on both sides. So, expected value of epsilon t plus 1 x dash t plus 1 I write now as expected value of epsilon t plus 1 x dash t a dash, this term, plus epsilon t plus 1 epsilon t plus 1 dash and b dash. Now, this will be equal to, what is this now? This a dash is a constant. So, it comes out. So, I will take expected value of epsilon t plus 1 and x dash t, which is essentially we are talking about the expected value of epsilon t plus 1 with respect to x t, and because epsilon t plus 1 and x t are independent, the expected value will become 0, because expected value of epsilon t plus 1 is 0, much the same way as we did for determining m 1. So, this becomes 0, this term becomes 0. Now, look at this term now. This term has expected value of epsilon t plus 1 epsilon t plus 1 dash and b dash. Now, b dash comes out. So, I will write it as b dash expected value of epsilon t plus 1 epsilon t plus 1 dash, which is essentially the variance, expected value of epsilon t plus 1 with itself, that is a variance. And because it is a vector, I write it as I b dash. So, b dash comes out, and I am writing this as expected value of epsilon t plus 1 epsilon t plus 1 dash. And therefore, the second term that we discussed in the earlier expression, namely this term can be written as the expected value, the expected value term can be written as simply equal to b dash. Now, we use this and rewrite our expression then. So, what was our expression? We were writing this particular expression now. This is m naught and this we have determined, and this is b dash. So, we write this particular expression again and then write this as m naught is equal to a m 1 dash plus this b, and this we have written as b dash. So, m naught is equal to A m 1 dash plus B B dash, in which we have already determined A, which is m 1 m naught inverse. So, A has been completely determined. So, we write m naught is equal to A m prime m 1 prime plus B B prime. Then using A is equal to m 1 m naught inverse, I write m naught is equal to m 1 m naught inverse, which is A into m 1 prime plus B B prime, and therefore, B B prime is equal to m naught minus m 1 m naught inverse m 1 prime. So, this is how you get B B prime. Remember, all of this exercise we have been doing to determine or to specify the coefficient matrices A and B. Once the coefficient matrices A and B are fixed, then your model is completely fixed, and we want to determine A and B from the data. To do that, we have defined m naught and m 1, both of which can be determined completely from the data based on the cross correlations at lag 0 and lag 1. Now, we are trying to get another expression for B also in terms of m naught m 1. So, B B dash is equal to m naught minus this is the expression that we got. Let us say that we write C is equal to B B dash. This is one matrix that I will write, which is a P by P matrix, P being the number of sides. So, I write C is equal to m naught minus m 1 m naught inverse m 1 dash. Now, from here you can see, if we write like this, the matrix B does not have a unique solution, which means it can have several solutions which will satisfy this particular expression, several alternate solutions, all of which will satisfy this particular expression. So, one of the ways is to assume a particular structure for the matrix B. And in this particular model, the MATLAS model, we typically assume B to be a lower triangular matrix. So, one method is to assume B to be a lower triangular matrix. What is a lower triangular matrix? From the principal diagonal, if you take, all the elements to the lower side of the principal diagonal matrix will all be 0, will all be non-zero, I am sorry. This is a lower triangular matrix. For example, you have this and all other elements on the right hand side will all be 0, right hand side and to the above the principal diagonal of that matrix. This is the principal diagonal and all of these elements will be 0 and all these elements will be non-zero. That is a lower triangular matrix. So, if you assume B to be a lower triangular matrix, then B dash will become an upper triangular matrix, where only the elements above the principal diagonal will be non-zeros. Then you write B B dash as the matrix B as well as multiplied by the matrix B dash. The matrix B is P by P matrix, matrix B dash is also P by P matrix, and therefore, C, which is equal to B B dash, is also a P by P matrix. Now, the elements of C, we write it as C 1 1, C 1 2, etcetera, C 1 P. Similarly, C P 1, C 2, C P 2, etcetera, C P P. So, the matrix C 1 1 C, the matrix C is completely determined by the from the data, because we know C as m naught minus m 1 m naught inverse m 1 prime. M naught is completely determined from the data, m 1 is completely determined. Therefore, m naught inverse can be got and m 1 prime can be got, and therefore, the matrix C is completely defined. The moment you have determined the cross correlations and the matrices m naught and m 1, the matrix C is completely defined. And therefore, using the C matrix, now we have to determine the matrix B, and that is the exercise we are doing now. Okay. Now, look at this. The first element C 1 1 will be equal to B 1 1 into B 1 1, which is B 1 1 square. So, I will be able to determine B11 as square root of C11. So, we will write this as B11 is equal to C11 to the power half. So, first I determine B11, then I go to B21, then I determine B22, then I determine B23, B31, B32, B33, come to next B41, B42, B43, B44 like this. All the elements to the left and lower side of the principal diagonal matrix I will start determining one by one using this expression. It can be done using a longhand multiplication of the matrices. However, we will not go into that in this lecture. I will give you the expression which comes out of that. So, B11 you straight away determine based on square root of C11. Then we go to B21, or let us say we first define all the diagonal matrices B11, B22 etc., BPP. The expressions for that are B11 is given like this, B22, C22 is given B21 the square. So, you need B21. For BK1 we have the expression BK1 is equal to CK1 by B11, all of which will arise from the expression BB dash is equal to C or C is equal to BB dash. From this when you multiply, these are the expressions that we are defining. First you determine the first diagonal element B11, then go to B21, determine B21, use B21 to get B22 which is C22 minus B21 the whole square. Once you determine B22, that means you have reached the diagonal element in the second row. Then you go to the third row, 3-1 you determine, B31 you determine from here, 3-2 you determine from here, then you go to 3-3. For 3-3 you have the diagonal element exercise like this, starting with the left top element B11, you go to the second row, define B12, B22, then I am sorry B21, B22, then go to B31, B32, B33, B41, B42, 43, 44 like that until every time you reach the diagonal you keep on determining the elements one by one starting with the leftmost element. So, all of these expressions can be used to determine all the P by P elements. So, this is for the diagonal elements and this is for the other elements in the kth row. So, k is equal to 1, 2 etcetera up to P. This determines a complete this defines completely the matrix B. What are the assumptions? The assumptions are that the B matrix is a lower triangular matrix, that is all the assumption is in that. Okay. So, what did we do? We started with a particular structure of the model and then we determined the matrix A as well as matrix B. So, our structure was x t plus 1 is equal to A x t plus B epsilon t plus 1, where x t plus 1 is a p by 1 vector and p is the number of sites. You are talking about multi-site generation now. So, p is the number of sites and x t plus 1 is the value of the flow at each of these sites. It is a vector at each of these sites in time period t plus 1. So, you want to determine in the synthetic generation situation, what is it that you want to do? You want to determine the flows at x t plus 1 at each of these sites, p is equal to 1, 2, 3 etcetera up to p, at each of these sites using the flows at site at time period t at the same sites simultaneously, which means at a particular site when you are determining, you are using the flows, the information on the flows during the previous time period at all the sites, and the matrix A, which is a coefficient matrix in this particular case, and the matrix B both will use the cross correlation structure as well as the autocorrelation structure. So, this is how the model preserves the correlation structure both space wise as well as time wise at the same site. That is, when we are talking about the time correlation, we are talking about autocorrelation, and space wise when we are talking about, you talk about the cross correlation from a site A to site B, also lagged one time step. That means, it is a cross correlation at lag 0 as well as cross correlation at lag 1, and similarly autocorrelation at lag 0 as well as at lag 1. Then it also preserves the mean, the standard deviation at the particular site. And this is a very useful, and in fact, in implementation, when we are talking about planning models and so on, it is an extremely elegant way of preserving the correlation structure of multi sites. Let us look at an example now, which means just to summarize this particular model, essentially what we do, we first calculate the lag 1 correlations as well as lag 0 correlations. You define the models, define the matrices M naught as well as M 1. How do we determine? We determine based on the observed data. So, you must have, if you are talking about annual flows, you must have annual flows at each of the P sites, and you must be reasonably justified in using the assumption that these flows are all normally distributed at all the P sites. Multivariate normal is the assumption that is involved, and then you determine epsilon t plus 1 from the standard normal deviate tables, and epsilon t plus 1 must be independent of x t. So, this assumption must be valid. Look at an example now, by which all of this procedure that I just mentioned is clear. We will take the annual flow at two sites P and Q. There are 19 years of flows. So, you have annual flow at site P, annual flow at site Q for 19 years. Now, we will demonstrate it by just generating two values, but the same procedure you can take it forward and generate for any number of values. And as I mentioned in one of my earlier lectures, whenever we are talking about synthetic generation of data, the data must be generated for a fairly long period of time. Typically, when we are talking about planning for water resource systems and so on, using let us say 50 years of data, 30 years of data, you should be able to generate 100 years of data, 150 years of data, 200 years of data, etc., because the water resources that we are putting in place are supposed to serve for next 100 years. Even if they are not physically meant to serve next 100 years, you still need to generate flows for several years, maybe in excess of 100 years, to examine the performance of that system in future, possible performance of the system in future. In fact, when we talk about reliability of system, resiliency of system and so on, we generate the data for as long as 500 years, 1000 years and so on, essentially to generate sequences which follow the same statistical properties as the observed historical flows, and then examine the implications of these flows on the water resource systems. And therefore, whenever we talk about synthetic generation of data, you must remember that you must necessarily simulate or generate the flows for fairly long periods, typically of the order of 100 years, 150 years and so on. In this example, I will just demonstrate how to generate the first two values, the same structure with the using the same procedure you can generate any number of values. As I mentioned, the data is used to preliminarily primarily to define M naught and M 1. Once you define M naught and M 1, you discard the data and then straight away start working with M naught and M 1. Also, the model is for standardized flows, which means the x t values here, these are the flows. The flows have to be standardized and then use the standardized flows in the model. And then when you get the model x t plus 1, you can obtain the original flows, original values of the flows, generated flows by destandardizing. That is, from x t is equal to x t, let us say x t standardized is equal to x t minus mean divided by standard deviation. From this you should be able to get back your x t values. So, let us look at how we do this. So, we get the mean and the standard deviation, then we get m naught. The mean and standard deviation are got from the data. M naught is defined as the lag 0 correlation, cross correlation matrix. So, you take the cross correlation at lag 0, which is essentially the covariance. So, you define R p q 0 as x p I, which is the flow in time step I at site p minus the mean of flow at site p, similarly at site q, and divided by n s p, where s p is the standard deviation at site p, standard deviation at site q. Using this you get m naught is equal to 0.796 and 1. Then m 1 similarly we define it as lag 1 cross correlation matrix between p and q. So, this is p p, p q, q p and q q. So, you get m 1 using this expression, this is just a lag 1 correlation, you get m 1 is equal to 0.302, 0.164 etcetera. So, you define m 1. From m naught you can determine m naught inverse. So, m naught has been defined here. So, you get m naught inverse. So, m naught inverse is 2.73 minus 2.17 etcetera. So, you get m naught inverse. M 1 is given, m naught inverse is given, therefore, you can get A. So, you A is m 1 m naught inverse and therefore, you get A is equal to 0.47 minus 0.21, 0.31 minus 0.37. Then we go to B. We know that to determine B you need the matrix C. So, you know that C is equal to m naught minus m 1 m naught inverse m 1 prime. So, m 1 is given here. So, m 1 prime will be this, you get m 1 prime and m naught is given, therefore, you can get m naught inverse here. So, m naught is given, m 1 is given, m naught inverse is obtained, m 1 prime is obtained, therefore, you obtain C. Now, this is C. All of these are 2 by 2 matrices. So, you get C as 0.89, 0.76, 0.76, 0.95. Once you get C, that means you have the elements here C 11, C 12 etcetera. So, C 11, C 12, C 22 all these elements are given. Then we first start with B 11, that is a left top element, the first element. So, B 11 is C 11 to the power half, which is 0.94. Then you go to B 21. B 21 is C 21 by B 11. I am using these expressions here. These expressions B 11 is equal to C 11 to the power half, B 22 is equal to etcetera, diagonal elements as well as kth row elements. So, I use these expressions because C has been completely defined. And the previous elements that we have just determined, we use that and then determine the next element. So, we determine start with B 11, then go to B 21, then go to the diagonal element of that row B 22, then go to the next row, define B 31 and so on if you have 3 sites. So, in this particular case we have only 2 sites. So, you have defined B 11, B 21, B 22 and it is a lower triangular matrix and therefore, all the elements on the upper side they are all zeros. So, we get B matrix as 0.94, 0.81, 0.54 and this element which is above the principal matrix, this is 0. This is how you define the matrix B. And once you define the matrix B, you can determine the flows for the next time period. So, x t plus 1 is equal to A x t B epsilon t plus 1. A has been defined, B has been defined, x t is the flow during the time period t. To begin with, you can assume this to be zeros here, and epsilon t plus 1 are the standard normal deviates. So, you can get epsilon t plus 1 at both of these sites. So, A is this matrix, B is this matrix. You need to start the simulation, you need this matrix. You typically assume all of these to be zeros and then generate it for t plus 1, that is the idea. So, you are generating at both sites p as well as q for the time period t plus 1 using the flows at site p and q for at the time period t. So, assuming this to be zeros, we can determine x p 1, initial values are considered at zeros, and these are obtained from your standard normal tables. So, E p 1 and E q 1 are obtained. So, these are the assumed values. Because these are zeros, the first term vanishes here, only the second term remains. So, x p 1, x q 1, these are obtained, that is at t is equal to 0. If you put these are zeros, you get x p 1 and x q 1, that is minus 0.126, minus 0.254. Remember, these are standardized values, therefore, they can be negative. Then we use these values now to get x p 2 and x q 2, this is 2, x p 2 as well as x q 2. We use the same expression. Now, x p 1 and x q 1 are defined, and therefore, you get x p 2 x q 2. Like this, you can go to x p 3 x q 3 using these two values, x p 4 x q 4 using the next values and so on. So, this is how we generate the standardized values of the flows for the next few time periods. So, this t can be for 100, 150 and so on, as I mentioned. From the standardized values, you can get back your flow values using the mean and the standard deviation. So, essentially then in today's lecture, we have completed discussion on the Matalas model. It is a multi-site generation model. Typically, it is used for annual flows, seasonal flows, and perhaps in some cases for monthly flows also. But the focus here is to maintain or preserve the cross correlation structure among several streams in the same catchment or in adjoining catchments, as well as the autocorrelation structure. Even when we talk about cross correlation structure, it is cross correlations at lag 0, which means at the same time, as well as at lag 1. So, we are talking about cross correlations at lag 0 as well as lag 1, and the autocorrelations at lag 0 as well as lag 1. The model also preserves the mean, the standard deviation, and these two correlations, cross correlation as well as autocorrelations. And this model is extremely useful for multi-site generation, which are typically used in cases where you development of an entire catchment has to take place, where there are several streams and then you would like to generate data on several streams. So, we will continue this discussion in the next class. Thank you very much for that.